Hi everyone, welcome to AI Crack channel. This is Akash Gangbar and today we'll be studying application of derivatives lecture 5. In this lecture we'll be talking about second order derivative test and few theorems. Okay. So let's begin a lecture with the second order derivative test for local maxima minima, obviously for differentiable functions. Right? Now let's say we have a function y equals to fx. So what do? We first differentiate it one time dy by dx and then equate it to 0 to find out the stationary points. Okay. So let's say I've got one stationary point as c, right? Now in this case, what we'll be doing, we'll be finding out double derivative over here. So we'll be finding out d2y by dx square and we are finding out at point C, right? So now what we are doing, we are finding out the value of this particular expression d2y by dx square at point C, right? What is C? C is a stationary point where we had equated dy by dx equals to 0, right? Now, once we are done with that, we are judging the sign of this expression. We are judging the sign of this double derivative. If that comes out as negative, in that case, we say we have a local maximum, right? That is a case 1. If we have that as positive, we say that we have a local minima. That is case 2. And case 3 is when d2y by dx square equals to 0. This is 0. That is our case 3. Now in this case, we say the test has failed. Okay. So in this case, we cannot make any conclusion from double second order test, right? We cannot do that. We can just do that for case 1 and case 2. We can make direct conclusions for case 1 and case 2. We cannot make any kind of conclusion for case 3. We say that test has failed over there. So in that case, we again have to rely on the first order test, right? Now, a lot of times people get confused by the sign of double derivative. If we have less than 0, then how can we say we have a maxima? If we have positive, how can we say we have a minima? There should be a way to remember that, right? So let's say we have a maxima like that. In that case, we say the curvature is pointing downwards. So we can say that d2y by dx square is less than 0, right? Now, if we have something of this sort, in that case, curvature is pointing upwards. So we can say that d2y by dx square is positive. So that's how you can remember it. Okay. And now let's solve this question. Find the points of maxima and minima of the function fx equals to 12x5 minus 45x4 plus 40x cube plus 40. Okay. Now we are going to use the second order test over here, obviously, right? So first let's find out the stationary points. So f dash x, that would be 60x4 minus 180 x cube plus 120 x square, right? So we have to equate it to 0 to find out the stationary points. So we'll be getting 60x square is common. We'll be getting x square minus 3x plus 2 equals to 0, right? So this gives us 60x square x minus 1 x minus 2 equals to 0. So we've got x equals to 0 or x equals to 1 or x equals to 2. We've got these 3 points as the stationary points, right? Now we have to find out f double dash, right? Because we are using second order test over here. So we have to find f double dash x. So that would be 240 x cube minus 540 x square plus 120, sorry, 240x, right? Now what we can do, we can take out 60x is common and we'll be getting 4x square minus 9x plus 4, right? Now if we calculate f double dash 0, we'll be getting as 0 only, right? Because we have x multiplied over here, right? If we talk about f double dash 1, right? So that would be 60 multiplied by 4 minus 9 plus 4. So that comes out as negative, right? If we talk about f double dash 2, we'll be getting 60 into 2 multiplied by, this is 4, this is 16 basically, 16 minus 18 plus 4. That is positive, right? So we have got f double dash 1 as negative, f double dash 2 is positive, right? So in this case, basically we have a case like this one, maxima. In this case, we have a case like this one, minima, right? But in this case, the test is failing. So for this particular case, we have to revert back to first order test, right? So let's do that. Our f dash was this one. F dash x was 60x square x minus 1 x minus 2, right? Now we have to talk about this point 0, right? So let's take a point over here, let's say minus 1 by 2, and let's take a point 1 by 2 over here, right? So f dash minus 1 by 2, that would be 60 into 1 by 4 multiplied by, this would be minus 3 by 2, and this would be minus 5 by 2, right? So this comes out as positive. So we have a positive slope over here, right? And if we talk about f dash 1 by 2, we'll be getting 60 into 1 by 4 multiplied by this would be minus 1 by 2, and this would be minus 3 by 2. So that is again positive. So we can see that we have got positive slope over here and positive slope over here. So we have got an inflection point, something of this sort. We've got an inflection point. Okay. And now let's talk about Rolle's theorem, which says if fx is a continuous function in closed a to b, if fx is a differentiable function in open a to b, and if fa equals to fb, then there is this at least one point x equals to c such that f dash c equals to 0, where c belongs to a to b open, right? Now this looks a little complicated. Let me plot it once. Okay, so this is a, this is b. Okay, now this point is fa and this point is fb, and both are actually equal, right? So let's say this point is fa equals to fb, right? Now let's draw a function which is continuous and differentiable between a to b, right? So let's say it looks like this one. We can see that it's a smooth function, that's why differentiable. We can see that we haven't lifted our pen when drawing this curve, that's why it's a continuous function, right? Now we can see that at this particular point we have a local maxima, which implies that f dash c equals to 0. Let's say this point is c, right? This point is c over here, right? So we can see that f dash c equals to 0 at that particular point because we have a local maxima, right? But it might be possible that we have drawn a curve which is enabling us to find out this point, right? It might be a bias. So let me draw one more curve over here. Let's say like this. So over here, over here, over here, over here, over here, and over here as well. So we've got multiple points, multiple c values where f dash c equals to 0, right? Because we're talking about at least one point x equals to c, right? So basically what is happening, if you're drawing a continuous and differentiable function, then slope of this particular point, maximum point, is coming out to be 0. It can be minimized as well, right? It can be over here as well, right? But let's just talk about this particular case. Over here we are having a maxima, and that's why slope is actually 0, and that slope is exactly same as slope of this particular line, right? And this is also 0 because both of these points are at same level, right? So this line is parallel to x-axis, that's why its slope also 0. So we can say that we must have a point whose slope is 0, which is equal to slope of this line as well, right? That's what Rolle's theorem is all about, right? And now if we talk about Lagrange's mean value theorem, LMVT, then we can say that this is a superset of Rolle's theorem. It's very similar, right? So let's again have these points A and B over here. So let's say this is FA and this is FB. In this case, FA and FB are not equal. So this is our FA and this is our FB, right? Now what does it say? It says if we join these two points with a function which is continuous and differentiable, in that case, we must have a point where slope of tangent is same as slope of this line, right? Slope of tangent at a point is same as slope of this line, and that point is between A to B. Let's say C, right? Now, how can we say that? Basically, what we are doing in case of Rolle's theorem, this point was actually over here. So what we have done is we have shifted this point over here, right? In that case, we were talking about slope equals to 0 for this particular line. In this case, we are saying that this slope is same as this slope at this particular point, right? Now, how can we calculate out this slope? We can do that with the help of delta y by delta x, right? So what is delta y over here? Delta y is nothing but fb minus fa, right? This. And what about delta x? That is b minus a, right? So our slope comes out as fb minus fa divided by b minus a. So this is what we have over here, right? So f dash c is same as this slope of this line, right? fb minus fa divided by b minus a, right? Simple. And now let's solve this question. In 0 to 1 closed, Lagrange's mean value theorem is not applicable to. Now, if we talk about LMVT, the two conditions are the function should be continuous and differentiable. In case of Rolle's theorem, we have to check fa equals to fb or not. In case of Rolle's theorem, we have these three conditions. But in case of LMVT, we just have these two conditions, right? So in all these four questions, we just have to check if the functions are continuous or differentiable or not, right? So basically, I'll keep this as homework because we have solved so many questions for continuity and differentiability, right? So let's end this lecture over here, and this is the end of application of derivatives. So let's meet for integrals, and thanks for watching. Okay.